So we're going to go ahead and take a look at 8.2 matrix notation and Gaussian elimination. Now this is going to go very quickly, so remember you can pause, rewind if something goes a little bit too quick. So we're going to look at the objectives, we're going to look at linear systems, matrices, augmented matrices. So really what a matrix is where we're going to start. Then we're going to get into how to solve systems of equations using matrices and putting them in what we call row echelon form or reduced row echelon form. And so first off, what is a matrix? It's a rectangular array of numbers, sometimes called elements or entries. They're naturally formed rows and columns, and so you can sort of see down this example, what we have is we have two rows. Remember, rows go left and right, and then we have three columns that go up and down. And so we want to remember it always goes row by column. And so there's an old soft drink called RC Cola. That's why we remember the R and C in that order. So make sure that you remember R and C. That's going to be applied for not just matrices, but also identifying the elements in the matrix. So notice that we identified this matrix with a capital A. We will use a little a to represent some of the elements inside of it and their location. So this matrix A is a 2 by 3 matrix. So we have 2 rows and we have 3 columns, and that would be the order of that matrix. Okay. Looking at more of the matrix and identifying the individual elements, notice that what I just mentioned, we're going to use a lowercase a, and then when it has a subscript, it has, in this case, ij. So that subscript, just like down here, we have little a, and we have a subscript 1, 2. And so what the 1 and 2 represent, the 1 represents our row, because it always goes row by column, and the 2 represents its column. So what we're doing here is it's almost like an address for these elements. So what I'm asking is what element, if there is one, is found in matrix A at first row, second column. So we go to the first row, which is, this is the first row, I'll put a line right through it. And then we're going to go to the second column. So this is column 1, this is column 2. And so when I do this, notice where those 2 lines cross. They intersect right here at that element, which is -9. So I'll erase these items now, and you can see that at the first row, second column, we have the element -9. So we can do the same thing if I say something like, what is a let's say 23. And if I say this, and we have the second row, third column. So we go to the second row, this is the first row, this is the second row. So we want to go to the second row, which is right here, and we go to the third column, which is the third column, this is the second, this is the first. So if we go to the third column, second row, what we find is that 0 is the element found at that address. So the subscript is simply an address. Now sometimes we'll get something that doesn't exist at all. And so if I gave you, let's say, a sub 31, that is the third row, first column. Well, if you notice here, we don't have a third row. Even though we have a first column, we don't have a third row, so it's outside of our matrix, and so this value does not exist. And so that is a possibility, is where the values don't exist if you don't have either the row or the column to match up. And so let's look at an example. First off, the first question is, what's the order of A? So this is matrix A, and remember it always goes RC Cola. So what we're looking for is rows, okay, and rows go left and right, so we want to know how many rows we have, and we'll put those in red. And so if you look here, what we have is we have 1 row, 2 row, 3 rows, and 4 rows. And so we have 4 rows, so that's our first value of our order, is it's going to be 4 rows by how many columns? And we'll put the columns in green, and notice here that what we have is 1 column and 2 columns. And so what we have is a 4 by 2 matrix. And so remember, it's always going to be row by column. That's going to be the key for you, is to remember that order. Don't flip-flop them, that would be incorrect. Then we have some addresses, a sub 32 and a sub 11. If we look at a sub 32, what we have is, again, the first number represents the row number, and the second number represents the column number. So we have the third row, second column. So what we do is we come back over here, and we go, this is row 1, row 2, row 3, and that's what we want, is we want row 3. And then what we want is we want column 2. So there's 1 column, there's 2 column. And so if I circle that, now notice where there's the intersection. What are we circling both? And what you'll notice is it's 0. And so the value found at this address is simply the value 0. And if you look at the last one here, we have a sub 11. That is the first row, first column. And so so what we have is we have right here, and what we find is that 5 is the value found at a sub 11. Moving on to augmented matrices. So now we know what a matrix is. It's simply a device that allows us to get organized and put in our values. Okay? And then they have addresses that we can identify. Matrices can also be used to solve systems of equations. And those are called augmented matrices. And so what we have is at the very bottom of the screen, you can see we have a system of equations that we've already learned how to solve through substitution and elimination. Now what we want to do is we want to be able to construct an augmented matrix so that we can solve that using what we call Gaussian elimination or Gauss-Jordan elimination. So first things first is that you really want to set up your system of linear equations in standard form. And so what you can see here is we have ax, and then our b is -7, so ax plus b, y equals c. And that's your standard form for a linear equation. And then you do the same thing on the bottom one. We have ax, which our a is -1, plus by, or b is 4, equals c. And so we stack those up in proper order. And so both of these are going to be in standard notation. Then what an augmented matrix does, a little bit like synthetic division, is we eliminate the variables and only deal with the coefficients and the constants. So notice our conversion over here, 3, -7, and -1. You can see 3, -7, and -1. In the bottom, we have -1, 4, 9. -1, 4, 9. Now some textbooks will use a solid line. I like using the dash line. It doesn't really matter. You'll see both of those. But the dash or solid line represents the equal sign. And so what we have down here at the bottom is you can see the first column ends up representing our x values. And so we have 3 x's and we have -1x in the two equations. The second column represents my y values, -7y and 4y. The dash line represents my equal sign. And these values, -4 and 9, represents my constants. And so every time we set up an augmented matrix, we want it to look like this form right here. And that's what you're going to really start with, is really setting these up. So if we look at an example, you can see the instructions say construct the augmented matrix for the linear equation. Our first step is to write equation in standard form. So if you look at this first one, this is not quite in standard form. It's really close, but not quite. So what we want to do is we want to go ahead and write this 2x, and then keep the y, 5y, but notice that my z should be over here with my variable, so I'm going to add 6z to both sides. Okay, so I end up adding 6z to the right side, which cancels it out over here, and I'll add 6z over here to get it in standard form. I need to also add 1 because my constant needs to be on the right side of the equation. So what you'll notice here is there's my first equation in standard form. If you look at the second equation here, it's really a couple of steps here. First off, I really don't want that 3 here. Now, there's a couple of things you can do. In this case, I can do 6 divided by 3 and 12 divided by 3. So we have a single term denominator I can stack and simplify. It's probably the easiest path to take on this problem. Let's say there's a 5 down here. Well, that doesn't really simplify when I stack. So what you want to do is multiply everything by 5. That gets rid of the division by 5 on the left side of the equation, and you're left with like 10 minus 5y on the right, and you can rearrange. But for this problem, let's go ahead and just cancel here. We're left with 2x. And then right here, we also cancel, and we're left with 4z. So I end up having 2x. And again, I need to move my y over to the left side so we can put this in standard notation. So we have it there, and then we have -4z. And that should equal my constant, which is 2 still on the right side. If you look at the bottom one, just a little commutative property is all I have to do. I'll put that one in green. It looks like the x I need to just sort of put first. My z needs to come last, so my y slides over. But that positive z, just a little commutative property. And what we have now in these 3 equations is I have 3 equations in standard notation. And so it looks something like that, what I have in the box. So what we want to do is we want to convert that into and we'll double check our answer here. But there you go. That should match up with what we have. And now what we want to do is put it in a matrix, an augmented matrix. So what we'll do is we'll steal all the x's, that will be our first column. All of our y coefficients, 5, 1, and 7 will be our second column. 6, -4, 1 will be our third column, and their constants. And don't forget your dashed line represents the equal sign. And so what you'll notice here is we end up having 2, 5, 6 equals 1. 2, 1, -4 equals 2, -3, 7, 1 equals 9. and there's our augmented matrix. Taking a look at another one like this one, now we go backwards. They give us the augmented matrix, and they want us to construct the equations that represent this augmented matrix. So remember, the first column represents, let's say, x. In this case, I made it a, just to switch the variables up. It could be x, second column, y, third column, maybe z and w, or something like that. And this is our constant. So I used a, b, c, and d. And remember, these are my constants. And the solid line right here is the equal sign. So we look and we notice we have 0 x's, I have 8y, I have negative, 8b, I have negative 3c, 5d, and then equals 12. So if we look at our very first one, we have 0a, 8b, minus 3c, plus 5d equals 12. Looking at the second row, each row represents an equation. So my second row is negative 9a's, 1b's, 0c's, 0d's, and negative 7 as a constant. So we'd write it sort of like that to start with. Most of us are going to skip this step that I'm showing you underneath the orange and go straight to the red, but this is our first example. The third row, or third equation, is negative 2a, 0b, 0c, 2d equals 5. Okay. Now if we clean that up, anything that has zeros we don't really need. So the first equation should just be 8b minus 3c plus 5d equals 12. If you look at the second one, we have negative 9a plus 1b equals negative 7. And then on the third one, you have negative 2a plus 2d equals 5. And there's our system of equations going from an augmented matrix back to a system. So again, that's something that you'll do on your practice and on the test as well. Here's an example pulled off of Vox just for you. And so let's look at it really quickly. If we look at the first one, I can't single term denominator and stack and simplify. So this would be a great example of me showing you how we can multiply everything by 5. So I end up getting 5y over here on the right side. When I distribute this over here, the 5's are going to cancel each other, so I'm left with just 5 plus 4x. Now that's not in standard form yet. I really need to get that x, keep it there, move my 5y over, and move my 5. So we end up getting 4x minus 5y equals negative 5 once I move things around. Looking at the second one, it isn't too bad, but it looks like I got to do a little bit of distributive property here with that negative 2. So I end up getting 4z, and then I get minus 2x, and I get a plus 12y, and that equals 0. Not quite in the right form, so let's write it in the correct form. So we get negative 2x plus 12y plus 4z equals 0. So there's our second equation. Looking at the third one, again, distributive property with the 3. So we end up getting 5x minus y equals 3x minus 18z. And we just got to get everything to the left side. It looks like our constant is going to be 0 as well. So I'm going to go ahead and subtract 3x, and I'll do that to both sides. And what you'll notice is I end up having 2x there. Goodbye, x's. Then my y looks like it's by itself, so I go there. And then I need to add that 18z to get that over here as well. And then that should equal 0. So then what we do is we'll come down here, and it says, okay, put that in an augmented matrix. So what we take is what's in the black, and we're going to steal all the coefficients and constants. Now remember, every row is an equation. So this is the blue equation right here. So this is the blue, this is the red, and this is the green. And then each row represents a variable. So we have x, we have y, we have z, and remember this is our constant over here. So we just need to fill those in for each equation. So our blue equation, we have 4 for our x's, we have negative 5 for our y's. Notice we have 0 z's, and then we have negative 5 for a constant. Looking at the red equation, what we have is we have negative 2 for our x's, we have 12 for our y's, we have 4 for our z's, and we have 0 for our constant. Moving on to the green, we have 2 for our x's, negative 1 for our y's, 18 for our z's, and 0 for our constants. And that would fill it in, and you would see that's where we're at with that one. Moving to the next problem, what we're going to look at is actually how to solve systems of equations using augmented matrices. Now there's a lot of math talk here, so just read through what you can, but really what we look at is really the H stuff, and hopefully you remember a little of this from Algebra 2, or pre-calc if you came from there. So what we want to do is we want to go ahead and use what they call Gaussian elimination, and we're going to start with what they call row echelon form. Now when we talk about row echelon form, really an easy way of looking at that is simply we have 1 in the upper left-hand corner, and then depending on how many rows and columns we have, we will have 1 all the way on the diagonal. Now everything below each one, it has to be a 0 then. And so those ones, and there's nothing below this one, so there's no zeros there. But you can see the triangle a little bit here. That triangle right there, that tells us we are in what we call row echelon form. So row echelon form means that row 1, column 1. So row 1, column 1. There should be a 1, and every value below the 1 should be a 0. So that's number 1 right here. Number 2 says row 2, column 2 should be a 1, and everything below it should be a 0. And then what we do is we repeat that. Now normally you'll have 3 or 4 at max for what you guys are doing, but what we got is row 3, column 3 should be a 1, and there's nothing below it. Now what's going to happen is, if you notice this bottom row is an equation. Okay, so this row right here is an equation. Notice I have 0 x's, I have 0 y's, and I have 1 z. So whatever value or number is over here, notice what we have is we have no x's, we have no y's, and I actually have just 1 z, so I'm going to write it like this, equals a number. So if I clean this up, then our z is simply that number. We just solved for, in this case, z. And then what we'll do is we'll use back substitution in order to find, let's say, our y and our x. But once we get into row echelon form, it's going to solve for one of my variables, whether it's z or sometimes it's y, if it's just 2 variables. And then we can back substitute in to find the missing one. So what allows us to do is once we get good at this, all we're doing is manipulating numbers rather than dealing with variables and numbers. Again, a lot like synthetic division, if you remember doing that a little bit. Okay. So if we look at some examples here, the matrix below is in row echelon form. And so you can see here there's our triangle, and that's what we're shooting for to put in row echelon form. So what this tells me is in the very bottom row, it actually tells me my z is 3. Now this one's very nice because it also tells you the y, because there's no x's or no y or z's. It tells me that my y value, 1y, equals, remember that equals 2 is the dashed line, and then it equals 2. So I actually got 2 variables out of this one. And then we look at the top sort of equation, the top row, and it looks like I have 1x plus 9y plus 1z equals 1. Well, what that allows me to do is if I know these two, then I can just substitute those in to find what x is. So 9 times 2 plus 3 equals 1. And you can see what we end up getting here is 18 plus 3 is 21 equals 1. And so x would end up being negative 20 for this one. So we would find our x, y, and our z fairly conveniently once it's in row echelon form. Now this one you got both of them, so that's nice. But we could do the same thing. We would take our z value and we'd plug it in here. And then we would take our x and z and we'd plug it into this one. So we would sort of work our way up through the equations. If you look at the bottom one, this matrix is not in row echelon form. You can see the first column is in good shape. We got the 1 right where we want it, and we got the zeros below. But we don't have the 1 should be here, and then the 6 should be a 0 as well. And then this 0 right here should be a 1, and it's not. And so that would not be in row echelon form. We'd have to do some work to get it there. Now, in order to solve systems and get to that point, we have to learn these things called row operations. And there's really 2 major ones. There is a minor one that we need to be familiar with that's not technically in these notes here, but so I want to mention it up top. And that is you can rearrange, let's say I gave you this matrix here, and I'm making it really obvious type of thing. So something like this. So when we are doing automated matrices and we're solving them, we want to go column by column. We want to start with column 1, and then we will go to column 2. So we want to go column by column. And then once I choose a column, you always want to find the 1 first. So you want to create the 1 first. Create the 1, then create the zeros underneath. Then create zeros under. That's sort of your pattern. We're going to go to column 1, and we're going to make sure we get the 1 in the right spot, which in this problem, the 1 should be in the upper right-hand corner, and it's not. It's a 0. Okay? There's a 1 down here, but not here. And so I need to either make this a 1, or in this case, what we can do is a third type of operation, and that is a switch of 2 rows. So what I can do is I can switch row 1 with row 2. And so in other words, this matrix can be rewritten. I'll write it right here and erase it in just a moment. I can put the 1, the 2, and the 3. So row 2 becomes row 1, and row 1 becomes row 2. Look how convenient that is. My first column is actually perfectly done. I can actually move to column 2. But now I've got the 1 where I want it, and then I would move on to the 0, which is already there. So technically my column 1 is done. And then I move to column 2, and again, we always create the 1 first, and then we create any zeros if we need it. So we go column by column, left to right, and we create the 1s then the zeros. It's very tempting to skip and go to another column and make a 1 first. You really need to stick with column 1 and make sure it looks 1 with and zeros underneath. Then we'll move to column 2, and we'll do the same thing after that. So it's column by column, create your 1 first, and then go ahead and create your zeros. So let's talk about creating our 1s. So to create 1s, what we're going to use is either division or multiplication to convert a number that isn't a 1 into a 1. Okay? You just got to remember we got to multiply or divide the entire row by whatever we're doing. So a real quick example, let's go to, and this will work out really nicely. So I'm doing that on purpose. And let's say our bottom row, we're just going to make something up here. Let's go 7, 6, and 5. Okay? We're not going to do much with the second row. I'm just making that up. But if we look at the first row, I really want this 2 to be a 1. Okay? And so I can make a 2 a 1 by simply taking row 1. Here's some of the notation you want to get. So R1 is row 1. That's this way, row 1. And I'm going to divide by 2. Another way of looking at it is row 1 multiplied by 1/2. So we're going to cut row 1 into halves. It's no different than having an equation where you divide both sides by 2. Now remember, that's what a row is an equation. So all we're doing is simplifying this equation. We just make sure there's a 1 right here at the beginning. So now what we have is we have 2 divided by 2, which is 1, 4 divided by 2 is 2, and 6 divided by 2 is 3. So we get that for our row 1. Our row 2 we haven't even talked about or touched, but notice we got the 1 right where we wanted. So finding the 1s really aren't too bad. We just want to use either multiplication or division. Okay, now where we can definitely use multiplication, just to show you a quick one, is let's say this is 1/3, and then we have like 2, and we have 3, okay, and down here maybe we have -4, 5, and -1. Again, we're not going to worry about row 2, but let's look at row 1. So row 1, column 1. So we always go column by column. So we're going to start with column 1. And what I need to do is I need to make 1/3 a 1. This needs to be a 1. So I can take row 1 and I can multiply that by 3. So in doing so, my row 1 becomes slightly different. The 1/3 times 1 becomes 1. That's what I wanted. 2 times 3 is 6, and 3 times 3 is 9. And then the bottom row we have not even touched yet. We'll talk about that in a moment, but now we've got the 1 right where we want it. The next step is to make the -4 a 0, and that's what we're going to look at next, is how do we achieve zeros, which are a little bit more challenging than 1s, but we can do it. Okay? So to achieve a 0, we're going to use the row that we just made a 1. That's going to be the key. What we had is a matrix, and let's say it was 1, 2, 3, and we just made this row right here, row 1. We made sure there's a 1 here. We just did that. So we're going to use row 1 now to help us. We're not going to change row 1. We're just borrowing it for a moment so that we can change row 2. So let's say row 2 is -2, -3, and -4. Okay, I'm just making that up. So what we do is we want to make -2 a 0. Remember, we're going column by column. And so we're still with column 1. I've got the 1 where I need it, but I need to make -2 a 0. That's my goal, make -2 a 0. So I'm going to go up to the row with the 1 in it. So notice row 1 has the 1 in it. So I'm going to steal row 1, and I'm going to, it's like elimination that we did with equations. I want to make this number exactly opposite of this one. Now you can make them the same and use subtraction, but let's go ahead and just do addition, just like we did with elimination. I want to make the 1 a 2, because 2 plus -2 is 0. I want to eliminate -2. So I'm going to take row 1 and multiply it by 2. Okay? So that's what we're going to do, is take row 1 and multiply by 2. So just out to the side, let's take row 1, and I'm going to multiply it by 2. So what I got was 2, 4, and 6. Okay, something like that. Now I take row 2 and I put it right underneath it. Okay, so it looks like this. And then what I'm going to do is I'm going to add these two. You can technically subtract, but we're probably going to add most of the time. And that way we can just, as long as they're opposites, it should go away. We did that with elimination when we did it just like in Algebra 1 or Algebra 2, but earlier. 2 plus negative 2 is 0. There's our 0. So what we're creating is a new row 2 down here in the black. I'm using row 1 to help me out, but I'm going to change row 2. So your notation looks like this. Row 1 times 2, okay, plus row 2. Now a lot of times you'll see it written like this, and so I like the second one. So I'm going to start using this type of notation. So I took row 1, I multiplied it by 2, and I'm going to add to row 2. Whenever you see this notation right here, what it means is I'm changing row 2. I am not changing row 1. Okay, I'm only using row 1. I'm only using. I am not changing. I'm only using. So when you see this notation, you can look and say, I'm not changing row 1, but I am changing row 2. So what I get here when I'm done is going to be my new row 2. So let's go back to our problem. So I'm using row 1, I'm adding it to row 2, and what I end up getting now is 1 there and 2 here. So this row 2 in black now becomes my new row 2. So remember, I did not change row 1, I just used it. I want to leave that 1 there, so 1, 2, and 3. But now my new row 2 is what I fit in here. So instead of negative 2, I have 0, I have 1, and I have 2. So the notation again looks like this. 2R1 plus R2. That is going to be, I'm going to multiply row 1 by 2, add it to row 2, and again I'm changing row 2. And now I have my first column is set. I've got my 1, we looked at that, and now we figured out how to make zeros. Now what I do is I move on to column 2, which this one's actually done, because the 1 is right where I'm at. You can see the triangle now. And that's in what we call row echelon form. So I actually know, remember these are x's, these are y's. So if you look at my second equation, my second row, I have 0 x's, I have 1 y equals 2. Remember this is the equal sign. So I just solve for y. And that allows me then to back substitute it in to find my x. Right? And that gives me my ordered pair. So that's just an example right now. Let's move into rearranging the order of the rows. I mentioned that, and just real quick, put one a little bit more obvious. We'll go really fast on this one. But I wanted to lead in with that because we sort of want to start with that. So let's say I gave you something like negative 5, 7, and 3. Okay, and then down here we have 2, 4, and 6. Now neither one's has a 1 in the first column. Okay, so negative 5 and 2. So remember, we got to go column 1. We always start there. And I need this position right here to be a 1. So you could divide the first row by negative 5, but notice you're going to have fractions everywhere. Okay, which isn't bad, but maybe it's better to switch the 2 rows. So what I can do is I can rearrange these 2 rows, because I look at row 2 and I say, man, if I divide by 2, that works out really nice. I don't have to deal with fractions. So row 2 is going to go first, and row 1 is going to go second now. And why that's helpful is now what I can do is I stay with column 1, and I need to make the 2 a 1. Okay, remember, I always start with 1s, and then I'll make this a 0. But what I'm going to do is I'm going to take row 1, and I'm going to divide by 2. So divide by 2, divide by 2, divide by 2, and there's my new row 1. 1, 2, and 3. Pretty easy to get my 1 right where I want it. Now the next step is to make my negative 5 a 0. And so we'll look at some of those examples, but to do that, what we do is we use the row with the 1 in it, so that's row 1. We're going to multiply it by 5 so I can add it to row 2. And that allows me to replace row 2 with the new row. Row 1 is not going to change, and then I should get 1 and zeros. So the key right now is you really need to focus on how do I make 1s, how do I make zeros. If you can accomplish that, you're going to be very successful with augmented matrices. So here's the different types of problems, and I want to make sure you see the notation. So this right here, they want you to rewrite a new augmented matrix. You're not really solving, you're just rewriting it. So notice what they have is negative 4 times row 2 plus row 1. So in this problem, I am not changing row 2. I am only using it, not changing. I'm just using it. If it helps, go down to the bottom and go ahead and say, well, row 2 is not going to change. So I'm going to have 1, negative 3, and negative 4 are my answer. What changes is row 1. That is the thing that's going to change. So I'm simply using row 2 to help me change row 1. So let's do that. We're going to do negative 4 times row 2. So I'm going to take row 2, and I'm going to multiply it by negative 4. So I get negative 4, 12, and 16. Then I'm going to add it to row 1. So here's row 1, the 4's and the 0's. And I simply add those two together. That's what it's saying. So what I get is I get 0, 12, and 16. This is now my new row 1. Right? I used row 2. I did not change it. I simply helped me to change row 1. And now I come down here and put 0, 12, and 16. I would click enter and I would be correct for this problem. Again, we're not solving on this one. But you can see if we were solving, a nice thing we could do is just a row flip. Okay, you can see we just flip these two rows and I've got a 1 where I need it and a 0 where I need it. Just make sure to flip the entire row because those are equations. Each row is an equation. If we look at one like this, you can see it gets a, this one actually has 2 here. I want to make sure you identify it. This one right here, there's a comma right there. So I'll separate these into 2 so you can sort of see them now. And so we'll do the blue one first. So if we look at this, we're changing row 1. So row 1 is going to change. But row 2 is not going to change. So row 2, I come down here, and I do not change it. You can look at the second problem. I'm changing row 3, but I'm not changing row 2. So row 2 is not going to change in either one of these row operations. So I'm going to just come down here and copy it. What I am going to do is create my new row 1. So I'm going to take 4 times my row 2. That's going to be my first problem. So I get 4, 12, negative 20, and 8. And then I take row 1. This will be interesting. Look at that. And then add these two. So what we'll notice is, look at my new row 1. It's just all zeros. Now we'll look at this when we're solving, but anytime you get a row of all zeros, you actually use your row operation of moving this all the way down to the bottom. And so anytime you get a whole row of zeros, that's actually a true statement. 0 equals 0, okay, if you think about equations. But we want to move that all the way to the bottom. But for right now, that's where we want to leave it. We're not solving anything, we're just rewriting these things. Now let's look at the red one. Again, I'm going to change row 3, but I'm going to take row 2 and multiply by negative 20. So I'm going to erase this. I'm going to take row 2, and I'm going to multiply by negative 20. So I want to get rid of that 4, sorry. There we go. So let's do it that way. So negative 20 minus negative 60. We got 100, a positive 100, and a negative 40. Now let's put row 3 right underneath it. Okay? And then we end up adding these two. That's what it says. Sometimes you can subtract, but both of these we're adding. So we're using row 2, multiplying by negative 20, add to row 3, and we should get a new row 3. So if we add these, we get negative 24, we get negative 59, we get 92, and on this last one, we end up getting negative 34. So we fill those in. Negative 24, negative 59, 92, and negative 34. And that makes up our answer for this one. You can see it's just an example off the box. Okay, moving on. Okay, now what we want to do is we want to actually solve one. So I want to show you what the problem is. The next slide will have it a little smaller. I'll show you real quick in the upper left. Same problem, but it gives me more room to write. So what Hawks is going to ask you to do is identify if you have no solution, one solution, or infinite solutions. And we talked about this with our notation. We talked about no solution is what we call an inconsistent system. One solution is called a consistent system on Hawks. And then infinitely many solutions is called a dependent system. Okay? Now, before you answer those three, though, I think we should answer the problem. It's hard to know which one of these three you're going to select. But when you do select, like no solution, you're done. One solution, they'll pop up a box, and you'd put your one solution as an ordered pair. Infinite number of solutions, a box pops up, and you got to put your infinite number of solutions as an ordered pair as well. So remember, that's x comma, and then whatever y is in terms of x. Okay? Or it could be x in terms of y comma y, okay, kind of thing. So we'll have to, we're working on that still. We're trying to get better at that, but that's what we're wanting to do. So first things first, we got to convert this system of equation into an augmented matrix. So let's go to a screen where we can do this. So what I'm going to do is I'm going to go here. Okay, and my first row is going to be my first equation. So notice what we have is we have a 1, an 8, and a 65. 1, 8, and then an equal sign, and then 65. That'd be my first equation. Looking at row 2, I have a 4, I have a 7, and I have a 60. Both of them are in standard form, so it worked out really nice. Now, to solve this, what we want to do is we want to start with column 1. Okay, we're not even going to look at column 2, just ignore column 2 and column 3. We want to look at column 1, and we want to make sure that we start with a 1 in the upper left-hand corner. Well, this one worked out really nice. It already is a 1. Step 2 is we need to make the 4 a 0. So we borrow row 1. Okay, so what we do is we come down here. Let's do the notation out to the side. I'm going to use row 1, but I need to make the 1 a negative 4 so that I can cancel that positive 4. I want these to be opposites. So I'm going to multiply row 1 by negative 4. And then I'll end up adding it to row 2. So that's my notation. So I'm going to take row 1 and multiply it by negative 4. So I get negative 4 times 1, negative 4 times 8, and negative 4 times 65. Okay, so 4 times 5 is 20. And then 4 times 6 is 24, plus the 2 is 26. And don't forget our negative. Then we have our bottom row, 4, 7, and 60. And we'll add these two together. And then what you'll notice is our new row 2, remember we're just using row 1, our new row 2 is 0, negative 25, and then if you add here, we get negative 200. And that's our new row 2. So let's go right below this. Remember, I did not do anything to row 1. I kept it the same, so it's 1, 8, 65. My row 2 is now 0, negative 25, and negative 200. Okay? So if you look at our column 1, we are successful. We got our 1 and our zeros below. So column 1 is done. Now what we do is we go to column 2. And we say, well, we always want to find the 1 first. The 1 should always be on the diagonal. So here, 1, this right here, this negative 25, needs to be a 1. So we're going to use a division to make 1s. Okay? So we use multiplication or division to make 1s. We do addition or subtraction to make zeros. And so what we want to do is we want to take row 2, okay, and we're going to end up dividing row 2 by negative 25. So row 2 divided by negative 25. Let's see what happens. Okay, I'm going to put the next matrix. So I'm not even touching row 1. It's in good shape. I'll just leave it as it is. Okay, and so we get here. So 0 divided by negative 25 is 0. See how that doesn't affect my first column. We want to keep that column that way. But negative 25 divided by negative 25 is 1. That's exactly what we want. And then what we have is a negative divided by a negative is a positive. If you had $2 and you had how many quarters? That's 8. So what we have is an 8 right there. Now notice what we have is we have our triangle. This is called row echelon form. So we're done with this problem because they asked us to use Gaussian elimination. Now they didn't say row echelon form, but Gaussian is the smaller of the two names. The second name is going to be called Gauss-Jordan elimination. That's longer. So when we talk about Gaussian elimination, we only need to put it in row echelon form, not what we call reduced row echelon form, which is longer. Okay? So we just want to get our triangle here. Now why is because if you look at the bottom row, that's an equation. We have 0 x's, I have 1 y, and that should equal 8 if I convert it back over. Now 0 x's is like not having anything there. And there's no point in having a 1 there. So look what we have. We have y equals 8. We just solved for y. So in our ordered pair for this solution, I know my y is going to be 8. Now to find my x value, you can either take this and just go back into one of your original problems up here and plug it in just like we did earlier. Okay? You can plug it in into right above. This is an equation right here. Row 1 is an equation. And so you're welcome to do that. It came from the first one anyway. So let's do that. So we have x plus 8 times my y is 8, equals 65. And you'll notice here, x is going to end up being 1. Okay? And remember, to check yourself, you can plug 1 in for x and 8 in for y, and we get 4 plus 56, which is 60. And so that checks off on the bottom equation, and the top equation works as well. I know I'm right using what we call Gaussian elimination. Put it in row echelon form. Okay? Now, here's another example of one. It's already set up properly, and so I'll go to the screen and I'll work through this one. Okay? So this one's a little different because we have to do a little work here. But let's go ahead and keep it as it is. I have negative 2, negative 4, and 4. And then the bottom one is 4, 8, and negative 11. Okay? So everything's lined up. I need my -2 to be a 1. I use division or multiplication, but I'm going to take row 1, I'm going to divide by -2. That should create a row with a 1 right where I need it. But I also got to do -4 divided by -2, which is 2, and 4 divided by -2, which is -2. So there's our first row. And then our second row we haven't touched yet. Okay, the next step is to create a 0 where there's a 4. So what that means is I'm going to use row 1, and I'm going to multiply row 1 by -4, because I want to go ahead and I want to make that 1 a -4. So when I add them, I should get a 0. But remember, I'm not changing row 1. So technically, I already know what my row 1 should be here. It's 1, 2, and -2. I'm just changing row 2 is what I'm doing. So, and then I add it to row 2. So maybe out to the side, you take row 1 and multiply by -4. So we get -4, -8, and +8. And then we have 4, 8, and -11. And I'm going to end up adding these. And there's my 0 that I'm looking for, 0. And then what we get here is we get -3. Now look at this statement. This one's a little different. Notice that we do not have a 1. Column 1 is done. Column 2, we're ready to make a 1. And I can't divide or multiply 0 by anything to make a 1. Now let's investigate this equation right here. What this says is I have 0x plus 0y equals -3. Now, think to yourself, if I don't have anything over here, wouldn't that be just 0 equals -3? Now, we've talked about this before. If I said 0 equals -3, I hope your response is simply false. And anytime you get false in math, your answer should be no solution. So there's an example of a no solution. So we've seen one example where you get a single answer, what we call one solution or consistent. We've seen an example right now where we get no solution or inconsistent. You probably know what we have is what if I get infinite number of solutions and how we do that. Okay. Now the last thing we're going to look at is Gauss-Jordan elimination and what we call reduced row echelon form. So I'll probably show you this, and then we'll probably end up working on it in class a little bit more, so that the video isn't quite as long, and you'll get a lot out of it. And the key is, as long as you can make ones and zeros, you can do this. It's not different, it's just more. It's not different, it's just more. Okay, so when they call Gauss-Jordan, see how long the name is? That means it's going to take us longer to get our answer. And we're putting things in reduced row echelon, not just row echelon, so everything seems to be longer. So what we have is we still have the ones on the diagonal, but instead of just having zeros underneath, what we have is we have zeros underneath the ones and above the ones. And what this allows me to do is eliminate any back substitution. So if you look at here, at this bottom one, remember this column represents x's, this one column represents y's, this column represents z's. So what this says is I have 1z equals 3. That's the bottom row. Look at the second one though. 1y equals 17. And then the top one says x equals -2. So notice I found my 3 solutions, and I could put them in order triple, and I didn't have to do any back substitution. So what reduced row echelon does is eliminates the back substitution. So we go column by column, we find our 1 first, and then we get our zeros. Then we go to column 2. We get our 1 first, and then we create our 2 zeros. Then we go to column 3, we create our 1 first, then we create our zeros. Once you do that, then you can look at your constants to find your answer on something like that. So we will end up looking at some examples. You can see we start here, and again, I just did it there. And so I'll do one, but you can see what we're going to do is you can see a little bit more advanced ones, and that we'll be doing in class a little bit. But let me do this one really quick for you, so you can have one example in your notes before we have class. Okay, so here we go. So let's write our augmented matrix. So we got 8, 6, -44, and then I got my dash, and then what we have is 7, 7, and -42. Now as I look at this thing, what I notice is this. If I divided everything by 8 to create the 1 right here, I would have some fractions. It's not a big deal, but I did look down here, and I noticed if I divided everything by 7, everything would work out pretty nice. So the first step I'm going to do is a row switch. So I'm going to go ahead and do 7, 7, -42, and flip-flop these two. And so just interchange them. And now what I can do is I can do row 1 divided by 7. That should allow me to create the 1 where I want it, which is right here. And then I can go from there. Then I get -6. So that worked out pretty nice. Now my next job is to stay in column 1. Remember, we're always in column 1. I've got my 1. Now I've got to make the 8 0. To make zeros, I I borrow the row with the 1 in it. So I'm going to take row 1, and I want to make the 1 -8, so I can add those two. So -8 times row 1, and I'm going to add it to row 2. So out to the side, let's do that. -8, -8, and then -8 times -6 is positive 48. And then what we have is 8, 6, and -44. And let's add these two. And this is my new row 2. Remember, I'm not changing row 1. Row 1 stays the same. I'm going to go ahead and write it so that we're not tempted to change it. But my row 2 becomes 0, -2, and 4. 0, -2, and 4. Okay, so now it's ready to move on to row 2. And so row 2, I got to create my 1 just like row echelon form. And so row echelon form, I need to make this a 1 right here. So I'm going to take row 2, and I'm going to divide by -2. That's how we make 1s. Use division or multiplication. Typically it's division. But what I end up getting, row 1 I didn't touch. So 1, 1, -6. And then row 2 I get 0, 1, -2. Now, technically we are in row echelon form. See the triangle? So I know y is -2. I definitely know that. And back substitution is what we do. But that's not what the instructions say. The instructions say use Gauss-Jordan elimination. So on the test, I'm going to be looking for, did you make a 0 up here as well? So we've got our 1, our 0, we've got our 1. Now I've got to make my 0 right there. So to do that, I borrow the row with the 1 in it. Remember, this has the 1 in it, and I want to make that a 0. So I'm going to take row 2, and I'm going to multiply it by -1. And then I'm going to add it to row 1. And again, I'm changing row 1. I am not changing row 2. So row 2 stays the same. So 0, 1, which is good. We already found y. Why would we want to change it? But row 1, we want to go ahead and change. So I'm going to do a little bit of the math. Let's eliminate some of this so we can see it. Okay? You can always rewind if you need to see it and pause anytime. But that will give us some opportunity here. So let's go ahead. And what I'm going to do is I'm going to take row 2 and multiply by -1. So 0 times -1 is still 0. That's the key, is that it shouldn't be changing row 2. 0 is not going to change row 1's 1. We want to keep that at 1. So that worked out really well. Then I got -1 and I got positive 2. So this is -1 times row 2. That's what I did right there. Okay? Now what I'm going to do is I'm going to add row 1. And I should get a 0. Perfect. I got a 0 right where I want it, and there's -4. So now my new row 1, so this is now my new row 1, is 1, 0, -4. This is what we call Gauss-Jordan elimination, and we're in reduced row echelon form. It tells me that my y value is -2, and it tells me my x value is -4. And we could verify that by plugging them in, but we would get one solution on one like that. So really, in the video, the only thing I really haven't shown you is some of the more advanced ones, where there's maybe 4 variables, something like that. And so it's the same process, it just takes a little longer. There's going to be a lot of 0s and 1s, so it goes a little quicker when it's like that. And you can see here, x, y, and z, there's 3 variables on one like this one. And the other thing that I haven't shown you yet for our matrix work is if you get a false statement, a true statement. And so we're going to be talking about that in class and let you investigate that and how to write your answers. But for right now, that's where we're going to stop this video, and hopefully you got some good out of it.